When teams move to microservices, the first thing that changes is not just how code is structured, but how many doors into that code suddenly exist. Every small service usually exposes an application programming interface, API, and together, those APIs become the main way data and behavior are accessed. This Tuesday Insights feature from Bare Metal Cyber Magazine explores how API security works in microservices architectures and why it matters when your environment is full of tiny, fast-moving pieces. The goal is to give you a clear, realistic picture of where the real risk sits and what it looks like when security is genuinely baked into those service boundaries instead of sprinkled on top. API security for microservices architectures is not a single product you switch on. It is a bundle of design choices, controls, and operating habits that shape how services talk to each other and to the outside world. You can think of each API as a door with a lock, a nameplate, and a camera, and API security as the way you decide who can knock, what they can carry in, and how you watch what happens. Network firewalls and host security still matter, but the most important trust decisions now happen where requests cross service boundaries. That is the layer where you decide which calls are allowed, which are blocked, and which need extra scrutiny. Because of that, API security lives across several parts of your environment at once. It has a strong identity and access side, since every decision depends on who or what is calling. It has an application security side, because you are validating inputs and protecting business logic. It also has an operations side, because it depends on logging, monitoring, and incident response to catch behavior that slips past the first checks. Instead of one big perimeter, you are creating many small perimeters by making each service responsible for a clear, well-understood contract. It helps to be clear about what this is not. API security for microservices is not just putting a web application firewall at the edge and calling the job done. It is not only scanning open API specifications or adding one security scanner to a pipeline and assuming all the services are now safe. It is also not limited to public-facing endpoints. Internal APIs between services often carry your most sensitive data and perform your most powerful actions, and they can be just as attractive to an attacker who finds a way onto your network or compromises a service. You will sometimes hear this topic blurred into broader phrases like microservices security or zero trust. Those larger umbrellas include container hardening, host protection, and how employees and administrators access systems. API security takes a narrower but very important slice of that picture. It focuses on how each request is authenticated, how authorization decisions are made, how inputs are validated, and how the resulting behavior is observed. When that slice is strong, the rest of your controls have a much better chance of doing their job. When it is weak, even a well-designed platform can be quietly exposed. If you zoom in on a secure call in a microservices architecture, the story usually starts with an external client hitting an edge gateway or proxy. That front door terminates encryption, checks basic authentication, enforces limits on how often someone can call, and decides which back-end service should receive the request. From there, the call travels through one or more internal services, each exposing its own API. At every hop, you want similar rules about identity, authorization, and input validation, instead of a different improvisation inside each codebase. The mechanics of API security are really about making predictable checks at every boundary the request crosses. Identity is the anchor for most of those checks. At the edge, the gateway might validate a token from an identity provider, a client certificate, or an API key. It turns that into a clear picture of who or what is calling, which roles they have, which tenant they belong to, or which application they represent. That identity is then passed along to inner services, either by forwarding the original token, minting a new token for the internal call, or embedding key identity attributes in headers that downstream services trust. When identity is inconsistent, missing, or too vague, every later security decision becomes shakier. Authorization and input validation are the next layers in that flow.
Each service should have simple, understandable rules about which identities or roles can call which endpoints, using which methods, and with what kinds of payloads. Some teams centralize this in a policy engine, so the rules are written in one place and reused by many services. Others encode it directly in each service, but standardize on a common library or pattern. Either way, every service boundary is an opportunity to reject requests that do not make sense for the business or that look malformed or abusive before they touch the most sensitive logic and data.
Observability ties all of this into a feedback loop. As requests move through gateways, meshes, and services, you want structured logs, traces, and metrics that describe who called what, from where, and with what result. That telemetry helps operations teams troubleshoot failures, but it also lets security teams spot anomalies, such as sudden spikes in certain calls, unusual sequences of services being chained together, or repeated attempts that fail authorization. When you can see a request's path across services, you are in a much better position to refine policies and respond quickly when something goes wrong. In day-to-day work, a few common patterns show up when teams apply API security to microservices. One very typical pattern for external clients is a combination of an edge gateway with internal services that are never exposed directly to the internet. The gateway handles encryption, client authentication, and basic threat filtering, while the inner services assume that any request they receive has passed those checks and focus on business-specific authorization and validation. For many organizations, this is the first step because it creates a clear single point to manage external access without forcing a redesign of every existing service. Inside the environment, service-to-service security patterns become just as important. Many teams move toward mutual encryption between services, where each service has its own identity and both sides verify each other before exchanging data. On top of that transport layer trust, they add application-level authorization based on the identity of the calling service, the environment, or the tenant. Over time, this often evolves into a service mesh or similar fabric where policies are defined once and pushed in a consistent way. That is a more strategic, higher-effort pattern, but it pays off in making internal APIs much more resistant to abuse or lateral movement. API security also takes on different shapes depending on the domain. A payment service might require stricter authentication, additional input checks, and tighter limits than a read-only catalog service. A data export service might enforce careful pagination and filters to prevent bulk scraping of customer data. Partner-facing APIs might have their own keys, usage agreements, and dashboards so that you can see how each partner is using your platform. Across all of these, the underlying move is the same. Understand the risk profile of each service, and then tune authentication, authorization, validation, and monitoring so that higher risk areas have stronger guardrails. When teams invest in API security for microservices architectures, they gain clearer and more enforceable boundaries around critical behavior. Each service becomes more predictable because it exposes a defined contract, accepts only the inputs it expects, and enforces access rules before doing anything important. That makes it easier to reason about risk, to bring new developers onto a system, and to change one part of the architecture without accidentally creating a gap somewhere else. The same observability that helps with security also shortens troubleshooting, because you can see exactly where a request succeeded or failed along the chain. Those benefits come with a real price in complexity and effort. You are adding more building blocks, such as gateways, identity providers, policy engines, schema validators, and sometimes a service mesh layer. Each piece has to be designed, deployed, kept up to date, and tested. Developers need time and support to learn the patterns, and platform teams need runway to create guardrails that feel like help rather than friction. There can also be performance costs if you add heavy authorization checks or deep inspection in the busiest parts of your system without careful tuning and measurement. API security is not a one-time toggle. It is an ongoing part of how the platform is run. It also has limits that smooth diagrams rarely show. An API security program cannot fix broken business logic. If a pricing service happily applies discounts in the wrong situations, strong authentication will not save you. It cannot protect endpoints you do not know exist, such as legacy paths left enabled or new services launched outside of the normal process. It depends heavily on core hygiene, like the quality of identity data, clear service ownership, and up-to-date documentation. When those foundations are weak, even well-chosen security tools and patterns deliver less real protection than they should.
When API security fails in microservices environments, it often fails quietly for a while before it fails loudly. One common pattern is an architecture that relies solely on the edge gateway, with strong checks at the front door, but very weak or non-existent checks inside the cluster. Over time, people add temporary bypass routes, leave debug endpoints running, or allow internal services to talk to each other far too freely. The diagrams still show a clean perimeter, but inside the network, almost anything can talk to almost anything else. In that state, a single misconfiguration or compromised service can open a path straight to sensitive data.
Another failure mode is simple inconsistency. One team uses tokens with clear claims, another uses raw keys, and a third invents its own scheme that only that team understands. Some services validate inputs thoroughly, while others assume upstream callers have done the work. Security reviewers then struggle to build a coherent picture, and automated tests do not cover all the different patterns. This kind of shallow adoption shows up as islands of good practice, surrounded by large areas where everyone agrees they will standardize later, often after something has already gone wrong. Healthy adoption looks very different in the details. Teams can produce an accurate list of their APIs and can point to which ones handle sensitive actions or data. Most services follow a small set of standard patterns for identity, authorization, and validation, so reviews focus on unusual cases instead of basic plumbing. Metrics show that obviously abusive traffic is rejected early and in the same way, regardless of which service it hits first, while legitimate requests succeed at a high rate. During incidents, responders can trace suspicious behavior across services and quickly see where it was blocked or allowed, without having to piece together dozens of unrelated log formats.
At its heart, API security for microservices architectures is about treating every request as untrusted and making deliberate, repeatable decisions at each boundary it crosses. Instead of defending one large wall, you are building a series of small, smart checkpoints that understand who is calling, what they are allowed to do, and whether the request makes sense in context. That way of thinking influences how you design services, how you assign ownership, and how you operate the platform over time. Once you see API security through that lens, it becomes easier to pick your next move. Investments in identity quality, consistent patterns, and clear observability often yield more value than another new security product. A practical place to start is to pick one important path through your system, such as a key customer action. Map the services and APIs involved and ask where trust is assumed instead of proven. The answers can show you where your architecture is already strong and where a small number of focused changes would noticeably reduce risk without slowing the work your teams need to do.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.